Welcome everyone. So this is our 86th live stream geometry. We have me and 5 other people here with me right now. And I am going to go over problems from the same geometry discussions and problems Discord server that I did last time. Looks like we have another person that just joined us. So if you'd like to join me in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. All right, so with that, I'm going to move to the first problem. So I'll share my screen. Can you all see it? Sorry, I didn't have time to put it in LaTeX, but this one looks really interesting. So you have a cyclic quadrilateral ABCD. So this one is a little harder because it's a riddle instead of a middle riddle. And you have any point M, and you take M and you project it onto basically everything you can think of: AD, BC, BD, AC, CD, and AB. So basically we draw the complete quadrilateral. And we have a point M that can be anywhere. And we draw the perpendiculars onto all these. So this and this, and this, whoops. So those two, these two. So I might as well draw the segments. So these two, and then these two, and then what are the other ones? The diagonals. So I didn't draw the diagonals of ABCD, but you also project it onto those. And basically you want to show the midpoints of those 3 segments are collinear. So a lot of perpendiculars here. So I'll make the diagram look a little better in just a second. But you want to show that the midpoints of all 3 of these are collinear. So we can hide a lot of the diagram here. Yeah, I really didn't need to intersect a lot of these. So I drew more than I needed. But yeah, we have all these perpendiculars and midpoints. And we want to show that the midpoints of these segments are all collinear. So let's see, midpoint, midpoint, and midpoint. And it looks like they're collinear. I don't think they pass, yeah, they don't pass through M. Let's make this a little bigger. So yeah, something like this. I kind of like that diagram. So we're going to want to draw MH because MH is perpendicular. And then G is perpendicular. This looks a lot like the Simson line, kind of, right? ME and MF are, yeah. Did I draw all of them?
No, this problem also would
But
not
like
be the
M is not on the circle, right? If M was on the circle, we couldn't just like spam Simpson line in it.
Yeah, if M was on the circle, it would be easy. It would just be the Simson line, right?
Yes, yes.
Yeah.
It's like a generalization kind of.
Yeah. Oh, what were you gonna say, Simon?
I wanted to say that this problem also kind of remind me of the Gauss line.
Oh yeah, the Gauss line. It kind of does seem like the Gauss line. Maybe it's a generalization of both. Maybe both the Gauss line and the Simpson line.
Mhm.
That's what it feels like. Okay. Hmm. Yeah, where should I start? So we have a lot of like cyclic quadrilaterals. So like if we intersect things, that like this would be a cyclic quadrilateral, and then this would be one, and this would be one. It looks like there's a whole bunch of them, right? So I should rename the points to be what they're actually in the problem. So S and T are, so this is S and that's T. So AD and BC. And then P and Q are this and this. And then K and W are this and this. And X is the midpoint of ST. And Y is the midpoint of PQ. Whoops. And K is the mid, or Z is the midpoint of WK. Yeah, this is a very tricky one. I feel like this one's kind of hard, but I'll try it for a little bit though. But a lot of these problems like this have like really, really tricky solutions.
Perhaps the Menelaus theorem could be here.
Yeah. Menelaus. Yeah, you have to find the right triangle. So
Maybe the triangle EMS might be the one we want to look on.
BMS.
TMS is, we want to prove, we want to prove that X, Y, and Z are collinear, so we might maybe find something there in the triangle TMS.
DMS.
It might be a line and find some ratio.
Interesting. But XYZ doesn't really intersect like the sides of DMS, right?
I meant T.
I have an idea.
Okay.
Let's O be the center of the circle inscribed ABCD.
Okay. Hold on one second. All right.
Yeah. Let's take the midpoint of AB and midpoint of CD.
Okay. So they're E and F, right?
Yeah. And take the midpoint of EF.
Interesting.
Then, yeah. Then G is the centroid of ABCD.
Okay.
Yeah. Then you take OM intersect the circle at M1.
Okay. So down here.
Yeah.
Okay.
Both on right, but you take it in the under one.
So you can call it M1.
Yeah. And then you take the actually I don't remember it in English, but it's the intersection of the perpendicular line from M1 to AB.
Okay.
The
The
projection.
I think that the Simson line. So so you have the perpendicular from M1 to AB, you said?
Yes.
Okay. That the foot of the altitude. Okay.
Yeah. You can name it E1.
Call it E1.
Yeah.
Okay.
And take F1 in the other side of CD.
Okay. Right. So I'll call that F1.
Yeah. Now take the midpoint of E1 F1. Call it Z1.
Okay. They call it G1.
Yeah.
Okay.
And now we have because OM and M1 are collinear, so we have EW on EE1 equal to OM on divide OM1.
Oh, because OE is perpendicular also, right?
Yeah.
Okay. Let me make this look better. Did you see this problem before, or you just thought of this right now?
I saw it before, so I will.
Oh, it's okay.
Right now.
You can keep going. You can keep saying the solution.
Yeah.
So I think it's a hard problem.
Yeah. Actually, it have two problem. The first one is true when M lies on the circle, and the second one is M on the plane.
Oh, so it was like a two-part problem.
Yeah.
Was this a
And
problem from Vietnam? Because I know Vietnam likes to do that, right?
yeah, it's on.
Wow, very cool.
Yeah.
All right.
So on the side we have the same ratio.
Okay.
Yeah. It mean that EW on WE1 equal to FK on FK F1.
Okay.
Yeah. So by the EIRQ lemma equal ratio on quadrilateral.
That means that G1, Z, and G are collinear, right?
Yeah. That's what I mean.
Okay.
Yeah. And it's GS over yes G1 is equal to EW over WE1.
Okay.
And it's equal to OM over M1.
All right.
We name it a constant K.
Okay, so EW over WE1 is GZ over ZG1, which is FK over KF1. And then what else did you say that was equal to? A constant?
OM over M1.
Okay. All right.
Yeah. And we take the similar. It means that G1 is with Z and XE is it means you take the another G2 and G3, then we have the same ratio.
Okay, so if you define G2 to be, if you take the perpendiculars onto these and like you'd have to define G2 and G3 the similar way is what you're saying.
Yeah, and let me write down in the chat.
Oh, what? Okay, so then we want to show G1, G2, and G3 are collinear, but is that just like the Simson law? So yeah, let me think about that. Okay, so okay, you wrote in the chat. Yeah, so G1, so we define G2 and G3 in a similar way, and then we get all those ratios.
I mean, if we can transform Z to G1 by the Homothety.
Okay, so yeah, so it's equivalent to showing G1, G2, and G3 are collinears, right? So okay, so we can assume basically we can assume this point lies on the circle because by the homothety that you just showed, it's equivalent, is what you're saying, right?
That's what I mean. Yeah, and that's what I mean.
Okay, yeah. All right.
So that is the pack 8.
All right, so we can just assume that this is on the circle, and then we would still have to prove it in that case, right?
Yes, yeah.
So maybe I could like draw another diagram, but now I assume it's on the circle. So actually, you know what if I just kind of drag this to be okay, so this is kind of what it would look like if this were on the circle. Let me draw this here. Okay, so yeah, then if it were on the circle, which I don't think I'm ever going to do it exactly perfectly, but that's pretty close, right? So then we'd want to show, like in this diagram, that that X, Y, and Z are collinear, right?
Yeah, and when M lies on the circle, we can use the Simson line.
Okay. So then we have WS, let's see. We have WSP are collinear.
Yeah.
Okay. What triangle is that the Simson line for? That would be the ADB, right? Yeah. So WS and P are collinear, and then
WQT.
WQT. And is there one more?
It's QS and K, QSK.
Okay. So we have WQ and T are collinear, and then WS and P are collinear. And then from there,
QSK at colonial.
Q, did you say QS and K are collinear?
Okay. Yeah.
Okay.
And TPK.
TDK.
Yeah.
TPK. Okay.
Yeah. And then we have the structure of the Gauss line.
Oh, wow. Wow. Did anyone from Vietnam actually end up solving that on the test?
It's a practice work problem, so I don't know.
Oh.
If this were to be on an live contest, I guess there will be really less solves.
What? Sorry, I didn't hear you that well.
I'm saying, like, if this was supposed to be an live contest, then I guess there would be less solves for this problem.
Yeah. If it's like a timed contest, I feel like that would be very tricky. But I don't know. There's a lot of really smart people, so yeah, maybe that. But wow, that's a really incredible solution. So all right, so I'm gonna go back a couple steps. So yeah, trying to think how to. All right, so I'm gonna write out the whole solution of that. Okay, so let OM intersect the circle at M1. Or first, let O be the center of the circle ABCD. And let OM intersect we'll call the circle omega. Let OM intersect omega at M1. Okay. And let E1, F1, and G1 be the perpendicular. Well, G1 is the midpoint. So I'll say let G be the midpoint of EF. Okay. And let so yeah, I didn't even define E and F. So let E and F be the midpoints of B. So yeah, this looks like it's overlapping a little bit. Yeah, let's draw something like this. Yeah, sorry, I'm gonna fix this a little. Yeah, it's so hard to draw a good diagram, but I'll get it in just a second. Yeah, all the points are squished together. I think that's good. I wish there was a way to rotate the diagram, but there's no way to do that. Okay. Let E and F be the midpoints of AB and CD. Okay, so let W, so we're dropping the perpendiculars, let E1 and F1 be the feet of the perpendiculars from M1 to AB and CD. So and then let G1 and Z be the midpoints of E1, F1, and WK. Okay. So then we have OE is parallel to WM. So to E1, M1. And that means that EW over WE1 is equal to OM over M1, which is equal to FK over KF1. And so by the gliding principle, O, M, and M1 are collinear. Or not collinear. By the gliding principle, G, Z, and G1 are collinear. Or you call it the ERIQ lemma. By the gliding principle, or ERIQ lemma, G, Z, and G1 are collinear. Okay. And then once we know that, then we can try to use a homothety. So we can define G2 and G3 similar to G1. Yeah, this is one of the hardest problems I've done so far on my channel. There's only a couple I feel like I've done that are maybe as hard as this one. So basically, therefore, X, Y, and Z are collinear if and only if G1, G2, and G3 are collinear. So X, Y, and Z are collinear if and only if G1, G2, and G3 are collinear by a homothety at G. Actually, I think we need one more thing here. So not only are they collinear, we also have those are equal to OM over MM1. So we also need so basically all these ratios would be equal to OM over MM1. Did I miss something here? Oh, I need another dollar sign. Okay. And okay, so we can reduce so we can reduce the problem to, yeah, so we can assume M1. Oh man, now these look all like 1 point. It's so hard to make everything look like different points. I think that looks good, right? There doesn't seem to be too many issues with that. Maybe something like this. And so now, yeah, we could do everything with M1. So OM1 and M, and sorry, draw this. Okay. So I don't know why it won't let me draw that. There we go. Okay, so once we know that, by the Simson line, we have a bunch of collinearities. So, whoops. Sorry. Yeah, my GeoGebra is not going so well today. But we have, okay, so we ultimately wanted to use the Gauss line. Oh, but I didn't draw G2 and G3. So I'll just say we can reduce the problem then to assuming M equals M1 lies on the circle. And then once we do that, then by the Simson line, we have a bunch of collinearities. So I'll write them all out. Okay, so I think it was was it W, X, and G are collinear? Let me see. So let's take triangle ABD. If you have triangle ABD, then W, S, and P are collinear. So we have W, S, P are collinear. And so are Q, let's see, if we do triangle ABC, then we have Q, W, Q, and T. And then we also have, so then if you do BCD, you have T, P, and K. And then we have one more. If we do CDA, then we would have S, K, and Q. So those are collinear. All right. And then once we know those, then it's the Gauss line. then X, Y, Z are collinear, or then X, Y, and Z are collinear because they are on the Gauss line of, let me see what it is, the Gauss line of TQSP. Wow. So yeah, even though I'm glad you showed us the solution, because yeah, I don't think we would have figured this out ourselves, but I think it's a very, very cool solution. So thanks for sharing it. All right, so I will move on to the next problem. Any questions on this solution? Anyone have any questions on it?
Could you please explain how did you get the ratio or the inequality GZ over ZG1 is equal to OM over M?
Yeah, so OM over MM1 is equal to EW over WE1, and it's also equal to FK over KF1. And then GZ and ZG1, those are all like halfway between those segments. So like, for example, I'm going to move, just temporarily, I'm going to move M. So EW over WE1 is FK over KF1. And if you go halfway, halfway, and halfway, then there's a theorem that says that, so GZ and G1, then there's a theorem that says that these will also be collinear and the ratio will be the same as those ratios. So yeah, I could send you a link on Discord. There's something called the gliding principle. I call it the gliding principle. Some people call it the ERIQ lemma, but it basically says that if G is the midpoint of these two, Z is the midpoint of these two, and G1 is the midpoint of these two, or even if it's not the midpoint, let's say it's a third of the way, a third of the way, and a third of the way, then you'd still get this ratio is the same as these two ratios.
Could we also say that not by the gliding principle or by Eric-lemma, or could we also say just by homothety? Would it be enough?
It's not exactly a homothety because we don't know the center of the homothety, so it's kind of like, it's similar to a homothety, but it's not exactly the same thing because yeah, I think it's a separate, I would say it's a separate theorem. It's not, it would take a little bit to prove, so I'm not going to prove it right now, but I could show you after the session like a paper that has this lemma. But yeah, it's very useful. So yeah.
Okay, great, thanks.
So yeah. All right, so I'm going to move on to the next problem. So this one I think might be a little bit easier. So let's see how far we can get. Looks like we have another person joining. When? So we have the triangle ABC, and then we have the end circle. So I'm going to draw that. All right. Thanks for joining, Nguyen. And it's tangent at B, and then I is this center, and X is on the altitude from A to BC. Okay. So I guess X, I don't know if X is the altitude or X is some point lying on the altitude.
X is like some point lying on the altitude, because like it is this kind of X lies on altitude from A to BC.
Yeah, so I guess X might just be not necessarily, I'll check it out. I don't think X has to be, yeah, I think it can be any point, but let's see. So M is the midpoint of AX, and XS is perpendicular to AB. Oh yeah, the point of tangency disappears often in GeoGebra when you change the diagram, so you got to be very careful. There we go. So XS is perpendicular to AD, and I don't know if S. So I might want to look this problem up. Actually, let me check this problem on Discord. So this is 199. So here is the Discord channel, and it's 199. So let's see what the diagram looks like. So yeah, X isn't necessarily the foot of the altitude. Okay, so S, yeah, S is just the perpendicular. That's what I thought. Okay. And then let me make it bigger. Sorry, I'm trying to make it bigger. It's having some trouble. There we go. Okay, so this is S. And MS, M is the midpoint of AX. And MS intersects AI at J. So something like this. Oh, that's too far away. I gotta maybe like that. So this is point J. And we want to prove that the circle with center J and radius JS is tangent to both AB and AC. That's interesting. All right, so I'm going to make this look nicer in just a second. Let's see, GeoGebra might not even think these are tangent. Yeah, yeah, I'll just have to draw it like that. Okay. Like this, like this. So we get this, this, and XTAIJ and XTJ. All right. And I don't want to make it look like M lies on the circle, so I wonder if it's worth, because M is the circumcenter of AXS, maybe it's worth drawing this circle. I don't know if that circle helps, but maybe it does.
Also, are the both circles tangent? Yes, they are. Can you just like try to move and see if they are tangent?
Try to move what?
Try to move C and see like if the triangle the circumcircle AX is and the other circle is tangent.
Oh, that if these two are tangent. Okay.
Yeah. Yes. Yes.
Yeah, point D keeps disappearing. It looks like they are. So if I move X, they are, but that might just be a homothety, right? And if I move,
Yes.
okay. So we can assume basically X and E are the same point if we wanted, right? Because it's just a homothety, right? Like, Well, maybe not necessarily. So, but let's see. It looks like they're tangent. Yeah. So yeah, it looks like these two circles are tangent. M, S, and J are collinear.
It's like the very definition of J.
Yeah. Is that so S
Oh
MS?
yes, it's like by Euclid you can just conclude that if MSJ are collinear, then these two circles are tangent.
Yeah. So basically,
Yes.
it's equivalent to just showing MS and J are collinear. Okay. So yeah, we can hide these circles. Is that, let's see if that's obvious. That MS and J are collinear. So J is the intersection of MS and AI. So let me, yeah, it's hard to get a good diagram, I'm sorry. But
It's like GeoGebra has its own configuration issues.
yeah, point D keeps disappearing, which causes everything else to disappear. So MS and J, MS, yeah, MS and J are collinear in the problem. So, and then AXS is tangent. Okay, so is it really that simple? Am I missing something here?
Like
Okay.
there is an lemma in Euclid's elements that states that if two circles are tangent, then the center and the intersection point is collinear.
Okay.
So like then
So
we can end with contradiction.
yeah, okay. So we know these circles are tangent. We just have to show that this is also tangent to AB and AC. Okay. All right. Yeah, so thanks for joining, Ruben. I know you joined a little bit back, but yeah, I don't think I said hi. So yeah, we have a good group of people. We have oh, Druva joined. All right. So, and it looks like we have another person joining us. Okay, so we know those are tangent. That's good. We just have to show that it's tangent to AB and AC.
Let ID cut the circle J.
Okay.
Cut.
So, oh, again at another point?
Yes, yes.
Okay. All right. I'll shrink the diagram just a little bit. All right.
Then JG is perpendicular to BC.
Okay. So that's by homothety at S, right?
Yeah.
All right.
And ID is perpendicular to BC too.
Okay.
Yeah. And we have the homothety center A.
Okay. It takes I to J, and then that solves the problem.
Yes.
Okay. So yeah, this problem is easier. All right. So I'm going to type up the solution, and then I'll see if I can move to a harder problem. So
I wrote it in the chat. Yeah, you can copy it if you want to make it fast.
okay. All right.
This was like an beautiful problem.
All right. So I'll copy what's in the chat. All right, so let's see. So yeah, I don't even know if it's really worth drawing this circle. Basically, we know that M, so I'll say let AS intersect the circle JS at G. G. Then a homothety at S takes AM to GJ. So yeah, MS and J. Okay, so a homothety at S takes AM to JG. So JG is perpendicular to BC. And so this means JG is perpendicular to BC. I'm going to move on pretty soon. And then, so A, B, and G are collinear. Yeah, I think this says everything, right? I'm just trying to see, am I missing anything? Or I think this is the, so you have a homothety at S takes this to this, and then a homothety at A takes that to that. Oh, so AI and J are collinear. That's the only thing. Oh, but no, we know that from the problem. Yeah, so I think this is all I really need. So I'm going to move on. Let me see if I have a, oh, this one looks kind of tricky. Let me see which of these I want to do. How about this one? So this one uses the mixed linear in circle. Actually, I'm not sure how hard this one is. We'll see. So O is the center. And I'll draw the in circle. And then I is the in center. And then I'll draw the mixed linear in circle. So I usually do it like this. Oh, I should have drawn the ray AI, not just the segment AI. Oh, whoops. Let me draw the ray. So that should be the center of the mixed linear in circle right there. So let's draw the circle. And its tangent whoops. Yeah, all I really need to do is do it this way. And then that's K. So I want to show that OI, BC, and XK concur, where the reflection of A over I is K. This is point K. And I usually like doing it. Yeah, let me do it. I think that's fine, actually. So let me make it like a tall triangle like that. Okay. All right. So we want to show that these three concur. Wait, that doesn't look OI. Oh, OI. Sorry, not DE. Let's make it a little bit farther away. Or I think that's good. It almost looks like symmetric. Like, are these angles equal right here? Let's see. Yeah, it looks like they're equal angles, right? I could check it. Wow, we've got 13 people. It's a lot. It's the most in a while. Yeah, how would I?
Y in some way.
Oh, what?
I'm saying like I think XK is symmetric to Y.
Oh, sorry. What? Say it one more time.
Like XK is symmetric to Y.
Yeah, it looks like these are symmetric. Like,
Yes.
yeah. So if I draw the angle bisector of this, it should be the same thing. Let me just make sure about that. Oh, I don't think so. Actually, I think it's very, very slightly different. So like if I make it like this, yeah, you can see if I make it a really obtuse triangle, then you can see it's not. Yeah,
Yes.
that's what you're saying. Okay. All right. So it's not symmetric necessarily. All right. Oh, you try to solve this, but you couldn't figure it out. All right. Let's see who's still on. Let's see. Who is their microphone on? Sorry. Hmm. All right. Yeah, so if these aren't symmetric, that makes the problem a little harder. So could we use the radical axis theorem somehow? Let's see who's still on.
Then which circumcircles would be like include to finish this by radical axis?
What did you say?
I'm saying like which circles then you would include to finish this by radical axis?
Oh, radical axis. Okay. And I intersect xi with ABC. All right. So yeah, that's the midpoint of arc BAC. That's a well-known theorem. Yeah, so what's the other circle? So we have this circle and this circle are tangent at x. So this would be one radical axis. And then we have, can we find another circle where this is a radical axis? Oh, you're right. XK is not tangent. You're right. So yeah, we don't actually know these concur, but I'm just going to draw it just if it helps. Yeah, we know this is perpendicular. One sec, I'll be right back. Let me get some more water. All right, thanks for waiting. Checking on BC in two different ways. Okay, so yeah, what's a good thing to project through? Let's see. Because yeah, if we let OI intersect BC at H, and we let XK intersect it at H prime, if we can show the cross ratios are the same, that would solve it. So yeah, maybe we could show that. So I think is JG let's see. Yeah, I don't think I need this. I don't think there's any point to this circle. Maybe it's worth drawing these points. And then I have AMIN is cyclic, and there's a couple theorems about that circle. Yeah, there's so many people on this. It's great, but yeah, in the beginning I was worried there might not be enough people, and then so many people came all at once. So yeah.
The main thing is like IGO is really near.
Oh, did you say you joined earlier or?
No. Like IGO is really near, so people are mainly focusing on GEO nowadays.
Oh, you felt similar, yeah.
Iranian Geometry Olympiad is like on 15th of February.
Yeah. Okay. I wonder, is AG Yeah. In is it some Olympiad like or am I participating in what?
Like he's asking if you are participating in Iranian Geometry Olympiad.
Oh, is there a GeoGebra Olympiad or is there some event on another website, a Discord Geometry Olympiad or something?
I don't know. I don't really know. It is our first time.
Oh. But yeah, if there's another event, send it to me, and yeah, I'll see if I can participate.
But you can like always live solve the problem.
Yeah. Okay. All right. Let's think about this. So OI, what do we know about the line OI? There's a couple problems. I haven't done a problem in a long time where I've used that line. So H, does H lie on the radical axis of these two circles? I guess I could check that. I don't think so, though. If we let G prime be the reflection of G over MN, then AG passes through H. Interesting. Let me do that in just a second. I wonder. Yeah, so I think H is on the radical axis of those circles, right? No, it's not. All right, so I'm going to check the lemma that you mentioned and see. So by projecting L, the antipode of L, O, and the point at infinity onto BC, and I guess what should we project through? We could project through I. And we could project them onto HK maybe, or onto BC. So HG and these 2 points right here are harmonic. Actually, no, because we have to project I through this midpoint of the arc. So it would be HG, this point, and this point. We could try projecting it onto the circle. Let me try Kahn's lemma. So Kahn says if we let G prime be the reflection of G over Mn, then AG passes through H. Interesting. So that seems like a useful lemma. Okay, so I'm going to draw that. That's not that complicated of a lemma. Oh, that's China. Okay. So I'm just going to assume that for now. I guess it's hard to prove.
Now you just need to calculate.
Just need to calculate.
Yeah, use Taylor's theorem. But yeah, it is a little complicated with the calculations.
Okay. What's Taylor's theorem? Oh, Thales, sorry. All right. I wonder if I've done it on my channel, because I don't know if I did China TST on my channel before. It's possible. Yeah. It's the part 2 of it. All right. I'll check it out after the session. So we have P is the midpoint of G prime G, and I is the midpoint of AK, right? So that means that IP, I don't know how useful this would be, but these should be collinear. Okay. So yeah, maybe I'll hide this one for now. But so So yeah, maybe there's some kind of homothety we could do to show that these are collinear, if we know that these are parallel somehow. So yeah, GG prime is parallel to AK. Yeah, so homothety at Q takes this triangle to this triangle. I wonder if there's anything special about point Q. I wonder, is the line? No, I don't think these are parallel. All right, looks like we have someone else joining. Sriyan Chota. So we also have AIK and the point at infinity are harmonic. And maybe we could project those through G onto something. The bundle GH XK GHXK. How do you know that's harmonic? Let's see. Because it would be OAL and G. Okay, so OAL and G. How do we know that that bundle is harmonic? Sorry if it's obvious. Okay, that's what you were saying with the antipode of L. Okay. So let me, so if this is the antipode of L right here, that's R. Then, okay. You're projecting onto BC. Yeah. Okay, so we need to show that's harmonic. So we need to show check. Sorry. So what does that mean in terms of angle? So we want to show GIHXK is harmonic. So of course this is the right angle. Is it the same as showing that this angle equals IGX is IGK? I don't think that's. Oops. Okay, so we want to show angle KGI equals angle KGX. Sounds like that would solve the problem, right? Because if we show that those are equal, then that would show that those are harmonic, right? We want to show IG bisects angle XIK. And that seems like an easier. Oh, is that actually true? No, I don't think that's true. Must have gotten confused. No, we don't want to show this is an angle bisector. We want to show, yeah, we want to show angle XGI is so yeah, we could draw it like this. Yeah, we want to show I lies on that. I'm going to draw XG. And maybe it helps to draw because XG meets it at the point where that's parallel to BC. So if I draw it like this, it's a well-known fact that AS is parallel to BC. Yeah. So yeah, I think we're very close. You have to prove B. Yes, exactly. So yeah, that seems like a lot. Yeah, we have to show that GC bisects SGK. Yeah, I agree. And then maybe we could use the lemma that Khan was saying. So we could define point Q to be like where IP, because this uses a lot of stuff from the Sharky Devil configuration, right? We could show that it's, instead of defining point K, we could define point Q as the intersection of IP and AH. We could show that it bisects angle QGS. I kind of like that better because then we don't need to use that KI as the midpoint of AK. So actually, now that I think about it, sorry, I and P are actually collinear. I, P, and Q are actually collinear with this point. So I don't know if that helps. Whoops. But yeah, it should be collinear by the Sharky Devil. And also, T, G, and R are collinear. Oh, the Sharky Devil configuration, it says that T, P, and I are always collinear. So if you draw the circumcircle of AMIN, where I is the incenter, and you let it intersect the circumcircle at P, then and P is the foot of the perpendicular from G to MN, then it says that P, P, and I are collinear. And you can prove it using inversion and a couple other ways. Yeah, you're welcome. And also T, G, and R are collinear. That's kind of also part of the configuration. So yeah. So yeah, we could try to show BC bisects QGS. Or is the external bisector. If we let, okay. So you reflect, so we've already used G prime here, but I could call it something different. Or it's, yeah, it's calling it G1 prime. I'll just call it, I'll just rename it as G prime and let the other one be different. All right. Then angle AG prime I equals angle KGI. By symmetry, okay. That looks useful. But AG prime intersects BC at the tangency point of the X center. Okay. And we know that this line is isogonal to AX. Okay. So, all right, so those are isogonal. How does that show that this is an angle bisect, or did you use the isogonal, oh, root BC inversion? So since those are isogonal, then BC is the bisector of KGS. So yeah, I can delete a lot of stuff in this configuration. Okay, so AG prime and AX are isogonal. That's well known. And then also, let T be the midpoint of BC. We want to prove that XGB, XGB equals ITG. Okay. I'm a little confused.
So if we intersect AG prime with ABC at the point, then we know that that point will be parallel to BC and as well to AS.
Okay.
So by symmetry, we get the angle conditions we want.
Okay. All right, so let G prime be the reflection of G over I. All right. And okay. So IGX is 180 minus IXG minus XIG. Okay, so I'm going to copy what you wrote. Oh, whoops, sorry, it didn't copy right. Certain things don't copy. There we go. Okay, so IGX is 180 minus IXG minus XIG, which is 180 minus half of arc LS minus XLR. XIG is XLR, which is 180 minus ARL minus XAR. And ARL and XAR. And that's 180 minus GIR. So ARL is GIR, G prime AI, which is IGK. Okay. So that's the angle chase, and then, okay. All right, so I'm gonna just type it up really quickly. Yeah, I can't copy paste the word angle or the whole thing messes up. So, but I'll do it quick. Yeah, we're doing problems from that server. Yeah. Oh, it's great. It's fantastic. Yeah. Oh, I thought it would space it out. Oh, well. I think I have to do it like this. Let's see if this works. Oh, you've never heard? Oh, you have to. Yeah. So I'll send it to you guys. So yeah, this Discord server is really, really good. Here's an invite link. But yeah, I hope you don't do too many problems on it so that I can do some of them on my channel. But yeah, take a look at it. It's really good. So yeah. Stefan sent this to me. So Stefan, he's not on the session right now, but he was the one who first showed it to me. Okay. So this is how we get the harmonic. This is going to drive me crazy. Let's see if that works. There we go. Okay. So this is how we get all those harmonics. Okay. I didn't copy right. Sorry. So we have this is equal to -1. And that means that I GHXK is -1. And oh, we know this, but we have to prove this. So wait, we know this is true because, yeah, you project through I. So then, you're welcome. So wait, this. So okay. All right. Sorry, you guys are smarter than me, but I'm gonna copy. Yeah, I'm gonna copy that. All right. So I think that's it. So this is by projecting L, O, and R through I. So I'll just say that. All right. So I'll move on to the next problem. So yeah, that wasn't as bad as I thought. So, but it was still pretty hard. Here's another one. So we have triangle ABC, with circumcenter O and 9 point center N.